welcome you all to SMU and to the Faculty Spotlight. And I'm going to present now Dr. Fred Olness, who's going to do some physics presentations.
Great. Thank you for the introduction. I'd like to introduce, I'll be assisted today by Professor Steve Sekula, who's going to help me out. But basically this is just an excuse to pull out some of my favorite physics demonstrations that we use in some of the courses here. And some I'll explain to you how they work, and some I won't. And you can either take our courses or ask your student how they work. But I'm going to start off with sort of one you've probably seen a bit before. And so I've got a set of dishes here, and a nice little tablecloth. I'll set this out on the tablecloth. And got a bottle of wine and wine glass and a coffee cup. It came with a broken handle. I didn't do that on this. And let's see. So which side does the spoon go on again?
You're asking a physicist?
Yeah. Apparently it was a bad move. But, okay, well, all set up over here. Okay, something like that. And so we're all set. And now, you got all set up at dinner, and you say, "Oh, wait a minute! I just realized there's a spot in the tablecloth." And you say, I want to change the tablecloth." You could, if you were a normal person, you would just take the dishes off and move them aside. But being a physicist, I tend to be a little bit lazy. There's something we like to minimize the action, which in physics actually has a special meaning. But I like to minimize my action and do the least amount of work I can. And so to do that, I say, well, gee, in principle, these objects, they have inertia. That's related. That's anything with mass has inertia, and I can take advantage of that. In principle, if I pull the tablecloth out from under there as quickly as possible, I should be able to pull the tablecloth out, and the inertia of these objects will keep them there so that they won't fall on the floor and go crash. Now, contrast that with, if I had done this with, say, a styrofoam plate and cup and bowl. These objects are very light. They don't have much inertia at all, and so that would be a disaster. But because these are nice and heavy, they've got a bit of inertia. So what do you think? Should we give it a try? And I swear this was broken. I didn't do that. All right. So let's give it. And actually, what do you think? Should I fill the glass? Yeah. Okay. All right. So let me see if I. All right. Now, who said that? Because if you're going to clean it up if I spill it, and since it was your idea. Do you think it makes it easier or harder when I put liquid in a glass like that? Seems to make it more, dangerous in the sense of making a spill. But in principle, does it increase the mass or decrease the mass? Increases the mass, should increase the inertia, and therefore it actually should make it easier. That's why I'm using a real plate instead of a paper plate. Okay. Now, if I were to come up here and do it kind of slow, what's going to happen then? Okay, yeah, crash all over the floor. Okay. But if I get it fast, hopefully that'll work. Okay. And I got to get it fast, but I've got to get it horizontal. If I pull it up, that won't work either. Then it'll still go fine. So okay, let's give this a try. All right. Okay. Give me a count. Here we go. 1, 2, 3, 4. I got to get really mentally. Okay. I should have practiced this. Do you want to do this?
Okay.
Oh, wow. Okay, great. Okay, I've got a victim. Okay, it's all his fault. Okay. All right, you just give it a good shot right down there on a nice 3 count. Down. Just really fast. Okay. And make sure you don't pull it up. Okay, on a 3 count. You ready? Here we go. 1, 2, 3. All right.
Yes.
Wow. Congratulations. Okay.
I've only ever seen it on TV.
Okay. All right. So physics actually works, and let me scoot this over. And if I can get you to just throw this in the back, we'll clean those up later.
As you can tell, I'm an assistant professor.
All right, and that can go I can go too. Okay. While we're doing inertia, we're going to try another one. And okay. Okay, this is a hammer. I've been told that I'm a theorist. I should qualify. Actually, Steve is an experimentalist, so he actually knows how to use one of these. But can I get a volunteer that someone that's used the hammer before? Okay, right here. Great. And tell me your name. It's
Barbara.
Barbara. Okay. All right. Great. Very brave person to volunteer without knowing what we have to do here. Okay. Now let me see. You've got a lead brick here. This is very heavy. Okay. Now let's see. Hold on. Let me get the directions. Okay. You get the hammer. It says you get the hammer. I've got a sandbag, and I've got a lead brick, and then I'm supposed to put my hand there, and then it says you're supposed to hit my hand as hard as you can, and because this lead brick is here, that'll protect my hand. Does that look good?
No.
No, okay. What you notice is the brick is upside down, right? Is that it?
No.
What's wrong?
I'll still hit your hand.
Okay. Let's flip it upside down again, but this time I'll put my hand under it, like that. How's that look?
Better.
Okay, all right. You want to give that a try? Okay. Now don't miss the brick. Okay. Ow! Just practicing. Okay, no, come on. Come on, really hit it. Come on, like you mean it.
I was.
I didn't feel it then.
Oh, it's lead.
Okay, it's lead, yeah, okay. Now, we just did the experiment. There are two possible conclusions you could draw. Okay, one is that this lead brick, because it's got a lot of inertia, is absorbing the impact, and I'm not feeling a thing. Or the other is I'm in a lot of pain right now, but I'm faking it. So those are the two possible conclusions. How can we figure out which is really going on? Oh, very good. We need a control. Okay. So then we switch places and do the experiment again, and we'll see. So, you see how brave you are. You didn't know this was coming up. Okay. So what I'd like you to do is slide your hand under there. Okay. Now, there's a, okay. Yeah, go ahead. Just, there you go. Okay, good. All right. Now you slide your hand under there. Now, there's a bit of a trick here because, sometimes when people do this, they flinch and the brick moves or something like that, and it gets kind of dangerous. So, I've been doing it a lot of times so I don't flinch. But what I want you to do is I want you to, so that doesn't happen, I want you to close your eyes so we don't miss that, okay?
Okay.
All right, very important, you close your eyes, and no matter what you hear, you don't want to open your eyes because they may move, okay?
Okay.
All right, so eyes closed, okay, close your eyes. Okay, and remember, no matter what you hear, do not open your eyes, okay?
Except I heard,
Well, what did you hear?
I know you switched something.
Oh, open your eyes, what? What I switch?
I don't know, but you switched, oh.
What?
Got a sledgehammer back there?
Where? Sledgehammer
Well,
where?
it's got a pretty long handle.
That,
Okay.
yeah. So you're very trusted, okay? Well, tell you what, we're not going to use this now, but I promise you we will use this before we finish today. So I'll put this aside for later, okay? And you can keep your eyes open now. Okay, you ready?
Mm-hmm.
Okay, here we go. Feel that?
Yeah, but not much.
Not much?
Not much.
More? No?
Well,
No.
I mean,
One more
feel the
time.
vibration.
Okay.
Pretty cool.
All right, well, let's give Barbara the hand. Thank you. So, yeah, physics work. I'm glad I got that brick turned around. Okay. All right. Oh, we're done. We're done with that. Let's see. Let's do. Since we're doing inertia. This is one. Anyone, I mean, you're going to the game, before the game you might want to get some burger and french fries. How do they make french fries? French fries are just, you take a long, thin potato and you deep fry it, right? Well, how do you get a long, thin potato? Well, the answer is this way. Okay, you take a straw and you run it through the potato, and then it cuts a piece of potato up, and that's how you make it. So we're going to make some french fries, and if you can help me pass these out. So I got lots of potatoes. Let's have you pass a couple around. Okay. Pass the shoe down. Okay, you got ready? Catch.
Wow, Rudy.
All right. Oh. I'm losing my potato once again. Okay. Okay. And what I want you to do is put the straw through the potato. Okay? Who needs a potato? Okay. So I showed you how it goes.
Oh, you like a better one? I can.
That's what it's supposed to look like. Okay? So you just put the straw through the potato.
We need a better potato over here.
We need a better potato.
Yes.
Better
Sheet
potato.
potatoes.
Sheet potatoes.
Here, you have one more.
They're brand new. Okay. All right. So you get it through? Anybody get it through? Okay. Give it a try. You might want to give them some extra straws. Let me get a couple extra too.
Who needs an extra straw? Whose straw is now extra bendy? Need more straws?
Oh, okay. That's what it's supposed to end up looking like. And I really you got through using a straw. I didn't use a drill or something. Okay. See, because you just, when you're done, you just pull out the, and there's your French fry. There it is.
I think we have some scientists right here.
Oh, okay. Ah, how do you do that?
Quickly.
Quickly. Okay. Quickly. Let's try it again. Okay. All right. Because this is the section where we're doing inertia. What I'm going to do is take advantage of the inertia of the potato, and I'll do this with a straw. I'll do it as quickly as possible, and hopefully get this through the potato before the straw realizes it can bend. So let's try this. 1, 2, 3. So right there.
Yeah.
Oh, there we go.
But you did it the easy way.
At the end.
Yeah. Let me see if I can get my aim better. Get a bit more in the middle. These are fairly thick. There we go. So if you get a running start, and actually I put my thumb over the end, that keeps the air pressure in there. It helps it from collapsing a little bit too. So yeah. But again, we're taking advantage of inertia. Okay. So how many French fries? Do we have a dozen French fries yet? Yeah, it'll take a while to, Oh, we just do it so quickly so that the straw goes right through. Right through. If you try to do it slowly, then it bends up. But it was just like when I pulled the dishes out from under underward. You do it very quickly, and it goes right through. And then I try to do it slowly. That doesn't work so well. If you try to do it slowly, it crunches up.
You got the better potato.
So yeah. Okay. All right. Let's try another one. Here's another mechanics one. And we're always trying to figure out if we can, especially as a theorist, we're always trying to figure out if we can predict what's going to happen. So I'm going to try to make these spool unroll. And the question is, if I pull on the cord, is the spool going to roll away from me or toward me? Okay? And so that's something in the mechanics class we sit down and try to calculate. So what do you think? How many think it's going to roll away from us? Raise your hand. And how many people think it's going to roll toward us? And how many people didn't vote in the last election? Okay, a lot of people on the fence. All right. So let's try it. Who said it's going to roll away? Okay, sure enough, you're right. Okay, it rolls away from me. Let's watch that again. Okay, you see it rolls away from me. Okay, all right. Who said it's going to roll toward you? Okay, see, it always rolls away from you. It never rolls toward you. Okay, it only rolls away, never rolls toward you. It only rolls away. Wait a minute. What's controlling that?
Which side of the center of gravity you're pulling on?
The angle. As I change the angle, I can make it roll away from me, or I can make it roll toward me. In fact, if I get it just right, I can make it slide without rolling at all. Okay, and so that's one I kind of cheated there a little bit. But we try to predict that, but sometimes you have to be careful because we don't always give you all the initial variables. And in that case, the angle makes a big difference. You can't answer that definitively without the angle. Okay. Let's do another one. Let's do, we're sort of going to start with mechanics and then do electricity and magnetism. That's kind of the order we teach things in. We're going to do some tug of war, and I could use about 4 volunteers for this one. If I could, no hammers involved, I promise. Okay. All right. 1. Need a couple. Need 3 more.
Great.
Please. 2 and 3 and. Give it a try. Thank you. 4. Okay. So now the game is you're not playing tug of war. Go ahead and pick up the rope. You're not playing tug of war against each other. But what I want you to do is pull the rope nice and tight. Don't wrap it around, and it's got to touch. It's got to touch these blocks. So you have to keep touching the blocks. Okay. And what you want to do is you want to pull it so tight that I can't reach down and touch the table. So the question is whether the 4 of you are stronger than me with one hand tied behind my back. Okay? Now you can't pull up, so it's got to be touching this. You can pull, go ahead and you can pull down. But okay. All right, let's try it. Here we go. 1, 2, 3. Give me as hard as you know. Try it again. Nope. Still touch. Pretty good, but I can still touch the table. Okay, take a break. So, I've set you up because I've got physics on my side, and this is a place where we teach about vectors because you're pulling that direction, but I'm pushing that direction. And because those are different directions, because force is a vector, even though you have a lot of force going in this direction, it doesn't take much force for me to be able to bend that rope down. Now, if you were pulling that and I tried to move that rope in the direction you were going, I was pretty tight. Of course, part of the trick is, I put these blocks far apart. What do you think would happen if I put these like that? Give me a little bit of tension. Do you think I could do it? See, yeah, no way. So the trick is, the trick is if I slide those far enough apart, then I have a very small angle, and the component in your direction is very small. So that's an example where I'm using vectors to my advantage, and you could have a lot of force on there, and I can still push it down and make it do that. So this is the part where in the course we play You Bet Your Grade. So some of our professors say if you can keep me from touching, you get an A. And it may look easy to the surface, but it's a lot harder than it looks. So great, thank you, appreciate that. Okay, let's try, while we're doing tug of war, let's try that one. So you want to get 2 more volunteers?
Can I have a couple of volunteers? All you have to do, all right, and I will gladly part with cash if you can do it, is pull these 2 hemispheres apart. All right, so this little sphere is made from 2 halves. All right, think of like an orange sliced in half. All you have to do is have one person grab this handle, another person grab this handle. You don't get to touch this, okay? And pull, all right? So who wants to give it a try? I will part with money. Because unlike a theoretical physicist, I believe in funding. I need some volunteers who want cash. Wow. We are not an economy-driven society. All right, I'm going to have to get some volunteers here. Fine. Professor Cooley, who I probably owe money anyway. All right, ready? Brace yourself. 1, 2, 3. We're married, so this is just the way we fight. It's okay. It's totally natural. All right. Well, I guess I don't owe you any money.
Yeah, I do.
Shall we make it easy? So what's happened is that all the air has been sucked out of the center of these 2 little halves here. And so you like to think, if you've got a vacuum that it's sucking something in. But what's actually happening is all the air has been pulled out of the center of this, and all the weight of the atmosphere, all the air that we're in and breathing right now, is holding these 2 spheres together. That's how strong the atmosphere is. That's how much force we're constantly under when we're in here. It's just that we grow up in it, we live in it, we don't notice it. Okay? So if I let air in, then the pressure outside and the pressure inside will equalize, and it'll be really easy. That's air going in to pull them apart. Okay? So all the weight of the atmosphere that we go through all day in our lives that we don't even notice because we just grow up in it. Okay? We're just all ready for this air that's weighting down on top of us. Can hold these two little spheres together if you pull the air out of the center of them. Okay? So just be glad your lungs don't do that all the time. Okay? All right, Fred, back to you.
All right. So let's see, we're going to try this next one. I've got a can of Coke and a can of Diet Dr. Pepper. Okay. Now, why would you drink? I mean, people generally agree this, the real stuff tastes better than the diet stuff. Why would you drink this if it doesn't taste as good, huh? I mean, what's the advantage of diet?
No calories.
No calories, all right? And no calories means you weigh less, right? So it must be that this weighs less, right? So seems right. Let's try it out. So we'll put this in the water, and that kind of floats down to the bottom. Put this up. Yeah, that floats. So it is less calories. It's lighter, right? Does that make any sense? No? But actually, I mean, there is a real reason. But the sugar dissolves in the water. It actually makes it denser than the diet. So that's not the reason it makes you weigh less. But the diet is less dense than the real stuff. And so but that's one we show that to students get them thinking a little bit. Well, let's see, that's lighter. So if I drink this, I won't weigh as much. So that's not the reason. But anyway, you can think about that. Let's try. Let's see. Let me try. Steve, can you run this around the front? And we're going to do a little. Let's hook that up. So it works. Okay. Any Rangers fans here? Okay. Yeah. You know how to throw a curveball? Okay. Good. Can you show me? Here, can you pass this up to him? And here, we'll give him another. Anyone else? No? Anyone else? In the back there? You can see why I'm not on the Rangers. Yeah, so, okay. All right, so go ahead. Let's see a curveball. Okay. All right, who else? Okay. Hey, yeah. Very nice. Okay. All right. Okay. So what's the trick? What's the trick to curveball? Yeah, spin. Okay. So I can't throw a curveball, but I've got a device here that will do it for me, and this is a homemade PVC. And what it does is the ball comes out here, a little bit of sandpaper, so the ball's going to roll along there and it gives a nice spin to it. And so this gives it a real nice spin. The reason I'm out in the ranges is I have no idea what direction it's going to come out. So here we go, we'll try it. And okay, and it has a definite curve to it. I could just predict where it's going to go. Okay, let's try it again. Okay, and you see I get it spinning like this, okay, and because as it's moving through the air, it's spinning in a particular direction, the pressure on one side versus the other side is different, and that makes it change. Go ahead, toss this back if you would. Okay. Where'd they go? And the physical principle underlying that is something called the Bernoulli effect, something we use when we design airplane wings and things like that, and we can take advantage of it here. And I should mention this during these demonstrations. There's some demonstrations that you want to try at home, like the tablecloth pull. That's a great one. Hi, thank you. This is my son Benjamin, and he's got some props for later on. Thank you. Okay, you want to do this one with the hairdryer?
Okay.
All right. Okay. Okay. Now he's practiced for a long time. All right. Got to get straight up. Okay. And you got to balance it real good. All right. See, very straight, okay? Because what's going to happen if he turns it over a little bit? It'll fall off, right? Turn it over a bit slowly. Stop, stop. Right. Try again. Just turn over a little and hold it. Just hold it. Straight up. Very stable. Just hold it and stop. It's actually quite stable. Let me try with the bigger ball. There's a Bernoulli effect making it spin. But it's amazingly stable. I mean, there's nothing under it. Let's try with it. Nope. Okay. I think we gotta go on this one. So I lied to you when I told you you had to get it lined up very carefully. It's actually quite stable, and you can tip it quite a ways over. Again, that's a Bernoulli effect because as the bowl moves over, it actually, the air going by makes a low pressure and it pulls it back. And so you've actually got something quite stable. So again, as I was saying before, some of these you can do at home. So go get your mom's hairdryer. She'll love you for us. Try this out. And the tablecloth one is another one you can try. Get Mom's Best China and try that out. But yeah,
Legal disclaimer, try nothing of what Fred says wrong.
Okay, all right, I think we're done with these toys. What's next on the list? Okay, let's go, let's see, helium balloon. If I can get that. And so we've done some mechanics ones. Actually, one of the courses I teach a music and physics course, which is a lot of fun because we have a fabulous music school and free advertisement. I have to come at the symphonies playing tomorrow night, and they are really outstanding. So if you get a chance to hear them, I recommend it. But it's a lot of fun because we have a lot of the symphony musicians come up and they take the science course. We teach them a little bit of physics, how their instrument works, and then we teach them, go through the instrument families. But one of the things we teach them is the fact that sound propagates through medium. So the fact that we're around here in standing in air is real important because the way the sound gets from me to you is my vocal cords make the air vibrate, and those vibrations move out to you. And of course, we could test that hypothesis if we took all the air out of the room. That would be one way of doing it. And I claim if you did that, you would have no sound. That would be true. But also, there's something else that's kind of useful about air. What is it?
Oxygen.
Yeah, that oxygen stuff. Okay, so if we took the air out, we'd be missing the oxygen. So that's not such a good idea. But here's an experiment we can do to show you that the medium matters with sound propagation. So I've got a balloon here, and you can probably guess what it's filled of. And so I'm going to replace the normal air in my lungs with the gas that's in this balloon, and we'll see if my sound comes out a little bit different.
What do you think? Do I sound a little bit different? Do I sound kind of like the chipmunks in that chipmunk movie? My voice is a little high, and as I take it down, as I get a little bit more air in here, you'll notice it starts to come down a little bit because I'm getting some of the gas mixed in with some a little bit lower. And as I take more breath, it starts to come back to normal. And one more breath, it comes back to normal. Try that one more time.
A, B, C, D, F, G, what to do for 5? Oh, shit, can you see? I can get the high notes, I can sing soprano this way. This is really neat. I guess my head gets a little spin now. This is helium and it displaces the oxygen, and the oxygen is kind of useful.
And kind of, whoa, boy. It gets you can get the high notes, but then that oxygen stuff is kind of useful, so you can't go too long without that. But again, hopefully that demonstrates that the medium is very important. In this case, we show that if we replace it by, in this case, of course, helium, you get something quite different. Another thing we teach about sound is that it's a transverse wave. And so, for example, if I take this ordinary rod,
if I get it vibrating in transverse mode, and maybe if you have real good hearing and sitting near the front, you can hear that. Okay.
Want me to tap it, Fred?
Oh, sure. Give it. Okay. So there you get the resonant frequency. But I can also get it going in a different mode. And I have this mark, so I can actually get harmonics depending on where I grab it. That's the octave. That should be the 12th.
What type of metal is that?
It's just ordinary steel.
Ordinary steel.
But I did cheat. Okay, beforehand, when you guys weren't looking, I took rosin and I put rosin over that. Now, who knows what you use rosin for? Any?
A violin bow.
Right. You put it on the violin bow because when the violin bow comes across the string, it grabs it. It's sticky. It's basically tree sap. And so before this demonstration, I coated this with rosin, so when my fingers slide down, it works just like a violin bow, and it grabs it just like that. If you had an ordinary steel rod, it wouldn't do that. But so I treated it with a little bit of rosin.
So it's an ordinary wrought iron, it's not stainless steel.
Just just got it from the hardware store. But the trick is you put a little rosin on it. We have score marks at the 1/4 and 1/3 point, because that's where that way I can get it vibrating in this mode. And if I grab it in the right place, that's what we call a node, because there's no motion where I'm grabbing it. But if I grab it at an antinode, then it just deadens it like that. And so very, very easily you can actually demonstrate where that is. Well, we're doing some sound ones. Let's try, let's try these. Okay. Benjamin, you want to demonstrate? Okay. And I'm going to demonstrate. Come out in the aisle so when you spin around you don't hit anybody. And here you go. And just come out so you're away from people when you spin it. And somehow I need one more. Okay? Just when you spin it, just make sure you don't hit anybody. Go ahead, show them how it works. Okay. All right. And go ahead. Come on, get some notes going there. What makes the sound? Yeah?
Yeah, I think it was.
What makes these things? Yeah. The ridges are important, yeah. I don't have a plane tube, but if you do it with a plane tube, it won't work. Okay. You think air's going through here? Yeah? Okay. How can we do it? Let me do it again. I'm going to spin around, and you watch and see if the air's going through. Okay? All right? Do you see the air moving? No, that was a lousy experiment. What can we do? How can we show that the air moving through there is important?
Plug up the end.
Yeah. So why don't you, if you have this, try it. Put your hand over the end, spin it around. Okay. Go ahead. Make sure you don't hit somebody. Okay. Put your hand, all right. Put your hand over the end, and then partway through, just take your hand off, and put your hand on. Yeah, okay. So covering it up stops it from working. So that's important for making it go, all right? So watching the air, that wasn't a very good experiment. But then you plug it up and you discover, hey, it doesn't work. Now, the question is, which way is the air going? Is it going away from me or toward me? Well, again, we can't see the air, so how can we do the experiment?
Flip it the other way.
You can't see the air, but we can put stuff in the air so that we can see it. Now, I just happen to have some little pieces of paper here, and so I'm going to spin it around, and we'll see. Either the pieces of paper will go this way, or they'll go this way. So let's try it out. And I'll duck down so I always pop myself in the head when I do this. All right? And so you can't see the air, but you can see things in the air, and so try it out. Okay, which way is the air going? Okay, so it's going out, all right? So we just determined that it's important that the air is going through it. The air is going in this direction, okay? And all by doing a few simple experiments. Now another experiment with this is you notice you get certain notes out of this. What's that sound like? Those notes.
Sounds like Close Encounters.
Yeah. And actually, if I had a little bit more control, I could get it, those are the same notes, I claim, those are the same notes as a bugle. So this is something very simple, but we can use this as a model of something a little more complicated. So, for example, this is very simple. This is a nice model for something like this. So I get certain notes out of this, and I get certain notes out of this. And we say, well, why do I get certain notes and not the other? If I try to get notes in between, it kind of clicks between notes, just like this. Somehow the notes on this are quantized, the notes on this are quantized. Well, this is very complicated. It's got vowels and all sorts of things. We don't want to analyze this if we can use this as a simple model to figure it out. And very often that's the kind of thing we do. So when we analyze the trumpet, we actually analyze it in terms of something very simple like this. Now, anyone ever play trumpet or brass or anything like that? Okay, yeah, a couple people. So one of the things when you learn about the trumpet, you learn how to take care of it. And one of the most important things about the trumpet is you never want to wash it in hot water, right? Because washing in hot water is bad. What if you have like a wool shirt and you wash it in hot water? What happens? It shrinks. Okay. Well, that's why you never want to wash a trumpet in hot water because they shrink. Okay. And then you get this. Very bad. Oh. Oil valves are easy.
So that's what happens if you don't clean the rest of the trumpet.
No, it's good. Gee, I oiled last year. Was it 3 months or 3,000 miles? Oh, this is, no, that's hopeless. We'll have to get by with one.
Clean your trumpet.
Yeah, so you can tell we pulled this out at the last minute. But so, of course, you notice here with the two instruments, they sound quite different. Even though they're both trumpets, they're both made out of brass, they're both trumpets. So they sound quite different. And even though they're both trumpets, because one's half the size of the other, they have a very different, what we call timbre or overtone series. And again, it's we can use the simple tube as a model of how that works. So let me try one more. We'll have it next time. But okay. All right. But I mean, that's an example how we can use simple models. So rather than saying, well, gee, this is something quite complex, we model it with something as simple like this tube, and it works out quite nicely. So, okay. All right, let's switch gears and, okay, what do we do next?
Electrocute the assistant professor?
Yeah, let's electrocute this, okay. Glad you mentioned this.
Yes,
let
I
me
am
drag-
too.
Let me drag this out a little bit. And this is an original from Dr. Frankenstein's lab. Okay. And if we're going to electrocute, we need a little power. I always get nervous working this one. Okay.
That power strip is also from Dr. Frankenstein's
Yes.
lab.
Right. Yeah, this is one we definitely don't recommend trying at home. Okay, let's see, Sarah, let's kill the lights and close the door. Okay, here, Ben, you work the lights. Okay, Ben, yeah. So, let's see. All right, that one, we'll do it. Yeah, okay. On and off that one. Okay, Steve, here you go. Right here, don't touch the metal. You betcha.
There's a noticeable anxiety in the room.
It's all right.
There's a notable anxiety in the room.
Oh, what's the worst that could happen? The burn-through rate with assistant professors at SMU is like 3 a year. I'll be
Okay.
fine.
All right. Okay, let's see. Nothing like open line current. All right, helps if I find the on switch.
Finally get to live my Star Wars dream.
Let's turn that off. Forgot our contact. Nothing like having a high quality permanent system there. Okay. Switch one is on. Okay. And we're ready. Kill the lights. Nice big spark going there. And slide your hand up and down. Don't touch the metal. If I move my hand up and down, you see it's actually conducting. The part beyond the hand is dark. Okay, lights on. All right. So this is called a Tesla coil, and this may seem like something that's esoteric. Turn the lecture fluorescence on too. It's basically like something esoteric that you can't use. But actually, how many people have a cell phone? Okay, you've got a little Tesla coil on your cell phone. Okay, it generates basically it uses induction to generate high voltages like that. Not quite. You're not going to electrocute yourself with your cell phone, but you've got a small version of this in your cell phone, and that's how you communicate with the tower. And one of Tesla's ideas was try to send electricity through the air, and you saw we got a pretty good spark going there. But although that's nice for demonstrations like this, you probably don't want, you don't be walking around your house and have great big sparks jumping between the power outlet and your TV or something like that, and have the dog run through it. So that would be a bad thing.
Or your natural gas line.
Yeah. So, but this is a nice one. It gets a good. The spark it's 30,000 volts per centimeter, so not quite 100,000 volts per inch. So we probably had around an inch going there. So it's around 100,000 volts basically going there. So it's a pretty nice punch. And fortunately, no electrocutions in this time around. So,
But if you come to my Physics 1308 class, I promise you I'll electrocute myself 30 times in one class. You can ask my students.
all right, let's try. Okay, let's go to the. Let's do the pickle rifle. Yeah. Okay. And then we'll need you on the lights again. Where did I put that? Okay, who remembers who invented the light bulb?
Trick question.
No.
Thomas Edison.
Yep, Thomas Edison, okay? And it was reported that when he invented the light bulb, he tried something like 10,000 different materials for the filament in the light bulb. And I think that's probably an exaggeration. He didn't actually sit in the lab trying 10,000 of them. I think he had his graduate students doing that. But we're going to try a pickle, and it's not recorded whether or not he actually tried pickle. Of pickles in it.
Not pickles.
It's not recorded in the history book whether or not he tried a pickle, but we're going to try a pickle to see if that would have made a good light bulb. Now these pickles, these are the finest pickles, Freestone pickles, original dill, cholesterol free. It's got the calories, fat, cholesterol, sodium. It doesn't say the wattage on here, so we'll have to work that out. And let me make sure this is off before okay. All right, let's try this out and see what happens. Okay, Ben, turn off the those fluorescents. Okay, and turn off my fluorescents. And if you hear a great big ow, turn back. Oh, there we go.
That's quality you can read by.
It's fried,
Turn my
fried
back on.
pickles.
Now, that didn't go very well, but there's one neat thing you can do with the pickle that you can't do with the light bulb. If you take it off and rotate it, put it back on, you can use it again. And you get all right. Yeah! There you go. 2 uses out of 1 pickle. What do you think the wattage on that is? Low. Yeah. The spicy pickles work better. I don't know why, but the spicy pickles seem to, oh, okay. Lights on. Okay. Well, they kind of work, but it'd be kind of tough doing your homework by that. Give me the whole lights. And so if you could kind of feel that, tell me right there. Is it warm? Kind of compare it to the end. The end's cold. And it's warm in the middle. Okay, I can pass it around. Please don't eat that. I'll pass it around. But it's actually where the electricity is flowing. Actually, it's heating it up. And the characteristic orange color, where have you seen that before? That kind of orange glow? Have you seen sodium vapor lamps? They have sort of the orange yellow glow. So basically, it's the sodium. It's the sodium in there that's making it go. And
You'll see that same color tonight walking home from the game, because I think all the lights around SMU are orange sodium.
okay. All right. I think we're. Oh, so we have to do some liquid nitrogen real quick. You get the new one?
Yeah.
So let's. One thing we deal with is extreme temperatures. Okay, we are prepared now in case anything goes wrong.
Well, I know what's coming.
All right, and I've got a little liquid nitrogen here. Before I go in, these test tubes are perfectly empty, but I'm going to set them in there, and you're going to find out that in about 5 minutes they're not going to be empty. And the question is, what were they not empty with? Did you get two of those roses? Are they on the? Oh, they're right here. Okay.
I didn't think you wanted to touch them.
And I'll take a balloon. And I'll use the gloves to preserve my fingers a little bit. So this is a new thing the physics department wants to market. It's freeze-dry balloons. Say they come in compact form, and you just take them out, they reconstitute, more or less. Let's see if it gets back in the original forms. Pass that around again. I'll give it a crack. Let's see if this one works.
We have very strange parties.
Oh, that one, there you go. Pass that around. So I'm going to try this with a rose here. Okay. Give it some time to get down a little bit. And these test tubes, let's see here. They started out with nothing in them, but now they have something in them. So how could that be? They started out empty. It's not condensation. What do you think it might be? Let's try this one. What's the air made of? Water. There's water in it, but not much. It's mainly made of
Nitrogen.
nitrogen. Okay, it's about it's mainly nitrogen with about a seventh or so oxygen. And so actually, what happened is the nitrogen in the air is condensing in the tubes, and so that's actually what you have in there. Now, I've got this rose just about down in temperature. So what I want you to compare is the sound of this rose hitting the table, a normal rose, with a frozen rose hitting the table. Ooh, shattered. Just shattered. So it makes it so brittle that it just actually shatters. Now, of course, those are they're like little pieces of glass. Of course, once it warms up, it'll be ordinary rose again. Makes a heck of a mess. But anyway, a nice sound when it goes. So, so that's quite. I'm not sure if it's useful for anything. But, all right, let me switch. Let's see. We've got two more left. So we're going to go to the bed of nails. And so I think we're ready with that. Can you, Ben, can you help with the bed of nails? And then
While you're changing every question,
yeah.
Nitrogen tires, help explain the theory behind why that is a good thing.
What's that?
Nitrogen-filled tires.
Nitrogen-filled tires. I'd have to, I'd have to, I'm not sure what the goal of that is. So let me get this put up there so just pile up on there.
Made in America.
Okay. All right, so let me check that out and see how we're doing. Actually, we've got, actually, while I'm doing this, we're going to make a banana split. So just put, you want to jump on the table? Put that up on the table. Okay, and well, that's going. You need a hand there?
Probably.
Ready?
Yep.
Now this has 4,000 nails in it, and I didn't count them, but one of our faculty actually nailed them in, is how he knows. And it's very, very heavy, and they're real nails. Yep, they're real nails. So, listen? Yep, okay. So again, I'm going to trust my life to physics. And because the idea here is that because there's so many nails, each nail by itself only has a very tiny area on the top. And you can come down and check these out later, but they're pointy. There we go. So each nail only has a little area on the top, but because there are 4,000 of them, I've got 4,000 little areas, and those 4,000 little areas add up to something quite reasonable. And so I'm able to lie on that without getting hurt. Okay. Now, of course, if you don't believe that, you've got to do a control. And so this is our bed of nails, and our control is what we call the bed of nail. And so here I have one, and this has a little tiny area, but because there's one of those, that's not got so much area. And so the pressure is actually the force per area. So although, so the pressure is what matters, and the pressure on that is going to be rather painful. So if you want to come down and try it, I recommend this one. You can send this quite well. Okay, and so let me see if this is going to work. All right. Okay. Shoot, this is, I should have worn something you could get blood on. Okay. You want to go home and get something?
You won't be around to worry about it.
Okay.
Don't worry about it.
All right. You want to slide that?
It's just like the tablecloth.
Oh, yeah. This is. Now, sometimes you pay a lot of money to go to those fancy spas that opens up your pores, and You come down to physics one, we'll do it half price. So, okay. So, Professor Sekula, are they sufficiently, is that good enough?
Yeah.
We done? Okay, thank you for coming, bye.
Who wants to see the hammer come out? Yeah, I know I do. Tenure's looking pretty good right now.
I guess I forgot, I promised that we'd use the hammer, huh?
Yeah, we did.
Okay, all right, we
Well,
promised.
you did.
Well, I should have worn my old tie then. Don't want to get, all right, go ahead. So, careful, let me get ready there.
So
Don't-
Fred, you know that when you hired me, right, my nickname when at my old job was Professor Butterfingers, right?
You should have told me, you should.
Oh!
Sorry. Ooh, that's, yeah, okay, all right.
Told you.
So just be more careful, it's the brick that hurts.
Yeah. Now, how do you want this brick? You want it up? Down like that? You want it like that?
Yeah, what do you?
How's that look?
Something like,
Does that look good to you?
that looks good.
What about the, oh,
Easy on that, easy there. That's, there's my chest over there. Okay. All right, I think we're done now. Okay, thank you. You can go.
oh no, I want tenure.
I don't think I'll be around to help you. Okay.
Oh, I don't need you, Fred. I've got this hammer. All right.
All right, let's get a 3 count. Okay, ready? Okay. 1, 2, 3. Ooh, that's smart. Where's the brick hold up?
Oh, it's broken. How are you feeling?
I kind of feel like.
Do I have to go to that faculty meeting next week?
Yeah. That's, all right, then do something good with that.
It's going to be department funds right there.
How's the tie?
Oh. Okay. Boy. So.
I thought you said there would be blood. This isn't any fun.
I think I'm kind of stuck. Oh. Okay, that's perfect. So actually, that wasn't bad. And if you want to come up and we've got the little one. If you want to try sitting on it carefully, you can try that out. But again, because there are lots of them, there's actually quite a bit of area, so the pressure works out. And again, you've got physics in your favor. So let me finish up with one last one, and let's move this table right up against here. Okay. All right. So, how many of you heard about us landing a man on the moon? Okay. All right. Supposedly that happened, right? But there's a problem because I don't think it happened because when you go up to the moon, you start off, you got to get in your rocket ship. So here's my rocket ship. And when you start off on your way to the moon, you start from the surface, you can push off the surface, okay? All right, and you turn your rocket on and you push off against the surface of the Earth, but then you get up in space. And space is a vacuum, and there's nothing out there. There's nothing out there for you to kind of move around with. You know, how do I move? I can't move anywhere. You can't kind of swim around. So there's no way to maneuver in space. How do I move? How do the astronauts move out in space? What do? You know, you shoot off a rocket, but it just goes against a vacuum. In fact, in the 1926, the New York Times had an editorial criticizing Robert Goddard because they claimed he didn't have the common sense that was doled out daily in high schools, that you need something better than a vacuum to push off against. So, you know, there's no way to move out there. How do you move? If I need to get to the end over there, I can't do it. How do you do it? How can I move around here? You know, I'm in a frictionless car, and I can wiggle back and forth, but I can't. How do I get to the end over there?
Use the earth to boomerang out there.
Use the earth to boomerang me. Yeah, what do you think?
Throw your shoe.
Oh, I could throw something back this way. Okay, I could throw something this way, and then Newton's third law says for every action is an equal and opposite reaction. So that would push me back the other way. So let's try that. Okay, I happen to have. All right, Steve, you want to get over there? Yeah. Okay, let's try this. All right. All right. So I'm going to throw this way, and the Newton's third law says I exert a force on this. There's an equal and opposite force. So I push this way, and I'm going to roll across the way. Okay, here we go. Ready? 1, 2, 3, go. How far to move? Garbage, right? So it doesn't work. The New York Times is right, Robert Goddard was wrong. They didn't go to the moon. Those are pictures of boiled oatmeal they brought back in some warehouse behind NASA. Okay, it was all a farce, right? You can't do it. Did we just prove it? What was wrong with that experiment?
Throw more force.
Ah, okay, I gotta throw something bigger. Steve, you got anything bigger? Over in the corner there.
Yeah.
Yeah, we got something bigger? What is fixing this? Oh, okay, we got, so the problem was I was throwing a styrofoam block, that wasn't very heavy. I gotta throw something bigger so that way I'll get more force and I can go. Okay, so what we're gonna do is I'm gonna throw this to him, okay? Well, you got a better one? Nope. Okay, does that look good? How many people want to do the experiment? Any ideas for a better one?
His name's Ben, right?
Yeah? Okay. All right.
I'm also not an athlete.
Okay. Well, what else could we do with this?
Use it?
Swing it
Yeah.
back and forth.
I could shoot it. There's about 5 pounds of CO2 in here, and it's got a nozzle velocity, something about half the speed of sound. And so that would be like me throwing a 5-pound weight at about 300 miles an hour or so. So that if you know that could be like throwing a lot more. So we'll see if it actually allows me to get somewhere. Okay. So let's back up here, and I gotta get in gear. You know how the Apollo astronauts they wear those Snoopy type gear things? So I got something like that. That's my astronaut headgear. Okay. And so what I'm going to do is I'm going to blast this off, and we're going to see.
Take the pickle with you.
If you can catch me. We're going to see if this works, and if they really went to the moon, or if that was just done on a Hollywood movie set. Okay, so here we go. All right. Okay, let's see. And first I got to get this, oh, okay. And so I take out the safety ring. So this demo is now completely unsafe. All right. Is this, by the way, is this one you do at home or one you don't do at home? All right,
Don't
yeah.
do anything Fred says at home.
Okay, yeah, this is one we don't do at home. Okay. All right, so I think I'm ready. So just like the astronauts will have a 10 count,